In this video, we will be discussing tree diagrams and the fundamental principle of counting. Let's begin by using an example of tree diagrams to discuss what tree diagrams are. Suppose you are buying a pair of earrings as a gift. You can buy them in gold or silver, and they can have either rubies, emeralds, or diamonds. What we're going to do is we're going to build a tree diagram to describe all of the options you have. A tree diagram begins with a box called a node. And the first node is the start node. Now from the start node, we will draw lines to describe the first decision we're going to make. For example, we could first choose which type of gemstone to put in these earrings: rubies, emeralds, or diamonds. So for each of these options, I would draw a line leading to another node where the node contains ruby, emerald, or diamond. The lines connecting the nodes are called branches. Now, from each of these nodes, for example, the ruby node, I could make the decision of either choosing gold or silver for the type of metal of the earrings. I could do the same for the emerald. And finally, I have the same options for the diamond. These final nodes are called terminal nodes. A path through a tree diagram is a way to get from the start node to any of the terminal nodes without backtracking. For example, that would be a path through the tree diagram, going from the start node to the ruby and from ruby to silver. Every path describes one of the final options you have for this decision. For example, the first path, ruby to gold, gives us one of the types of earrings: a gold earring with a ruby. The second path, a silver earring with a ruby. The third path, a gold earring with an emerald. Then we have silver with emerald, then gold with diamond, and silver with diamond. So each path through the tree represents one of our final outcomes. This accomplishes two things. One, we can count the total number of final outcomes by counting the total number of terminal nodes. There are 6. The other is we can list all of the different final decisions we can make, as are listed here. At this point, you should look in your textbook at the example that is similar to this one. You'll notice that in the example in the textbook, the type of metal is chosen first, then the type of gemstone is chosen second. But notice that we still have the same 6 final outcomes. Tree diagrams can become large very quickly. Imagine, for example, trying to create a 6-character password, where the characters are either lowercase or uppercase letters. The first decision you would need to make is, what is the first character of your password? Well, there are 26 lowercase letters and 26 uppercase letters for a total of 52 decisions you could make. So your first decision creates 52 nodes. From each of those nodes, you need to choose a second letter. That's another 52 nodes. Already this diagram is too large to draw. So we need a more efficient way to count the total number of decisions that can be made in the end. That is, we need to find a convenient way or an efficient way to count the total number of terminal nodes that would have been generated by our tree diagram. Well, let's look at the example we just did and see if we can't figure out how this would work. Our first decision was what type of gemstone to put in the earrings, and we had 3 options. So that created 3 nodes at that stage in our decision-making process. From each of these nodes, we created 2 more nodes. So we created 2 nodes 3 times. That's multiplication. Which gives us that at this stage we had 6 total nodes. Now that was our final decision, so this gives us our total number of terminal nodes, 6. And you could imagine if we had decisions to make from here, we would simply multiply by the number of options given in that decision. This gives us the fundamental principle of counting. Given a collection of decisions to be made, the total number of possible final selections or outcomes can be found by multiplying the number of choices for each decision. This is what we did in the previous example. When we were trying to count up the number of terminal nodes, which represent the number of selections or outcomes, we multiplied out the choices for each decision that needed to be made. Let's look at another example. Suppose I want to create a 6-character password. The first 5 characters have to be letters, and the last character has to be a number. And let's suppose that this password is not case sensitive. Then I need to make 6 decisions. When doing this by hand, it's a good idea to have a technique for doing this. We can draw a box for each decision that needs to be made. So we have 6 decisions. The first decision, and it's good to label the boxes, is to choose a letter. And then a letter, 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 and finally a digit. In each box, we'll write in the total number of options or choices we have for that decision. For example, the first letter of our password can be any of the 26 letters available. The second letter, any of the 26, etc. And finally, we need to choose a digit. Now you can count carefully. There are 10 digits to choose from, 0 through 9. So we write 10 in there for the 10 options that we have. Now if we multiply all of this out, we'll find that there are quite a few final passwords we could have come up with. In fact, there are 118,813,760 different passwords that have 5 letters, where case doesn't matter, followed by a digit. Suppose we're still trying to create a password, but we're told that we can't use the same letter twice. Then again, we still have the same 6 decisions to make. They're just a little different. We have to choose some letters, and we have to choose a digit. Underneath, I'm going to put NR to remind me that I'm not allowed to repeat these. So, for the first decision, there are 26 letters to choose from. Once I've used up one of the letters, the second character only has 25 options available to it. Then 24, 23, 22, and there are 10 options for the digit, which, if we multiply these out, gives us 78,936,000 different passwords. Suppose now that we are creating the same password, but now we need 3 letters followed by 3 digits, where the first letter is a vowel and the second 2 letters are not vowels, so are consonants. How many different passwords could we create? And again, assume that we cannot repeat anything in this example. Well, we have still 6 decisions to make. We were told we need to choose a vowel followed by a consonant, and then 3 digits. We're not allowed to repeat anything. So, first, we have 5 vowels to choose from. There are 21 consonants to choose from, and since we're not allowed to repeat, we only have 20 left to choose from at this point. There are 10 digits. Once we've used one up, that leaves us 9. Now we've used 2 digits, that leaves us 8. Multiplying this out, we find that there are 1,512,000 different passwords we could create. Notice that the more restrictive our passwords are, the fewer passwords there are.